The first type of graph we're going to talk about is an exponential graph. So the exponential graphs that we're going to see are always going to follow this form. So you're going to have f of x equals coefficient, and then a number that's to the power of something. We might see it just like this. But remember, that's pretty much the same thing, right? So if you had a y instead of f of x, it's the same deal. We call these exponential graphs. There's some rules to these exponential graphs. A and B can't be 0. If they were 0, it would make the question useless, because 0 times something would be 0 as well. The other rule is that B has to be a positive number in all of our graphs that we do. We're going to graph some of these and look at them and observe them and see if we can't figure out what A and B are actually doing to our graphs, and try to see what these graphs actually look like. So first off, I want you to make sure your window is at -10 and 10, because that's our standard window. And then I want you to graph y equals 2 to the power of x and see what happens. So I'm going to go 2 to the power of x. My window is my standard window. I graph it. And it should look like looks something like that. This is what our exponential graphs are going to look like. They're going to have these like sharp up curves, and sometimes they're going to have sharp down curves, and we're going to see when they have which. This one would be a sharp up curve, so we would call this exponential growth. So as your x value increases, your y value is increasing much faster. So if you notice, as I go, it starts off pretty slow, and then once I go up to like 2 or 3 or 4, I take a sharp increase up. We call that exponential growth. If you're looking at this graph, you should notice a couple things. The y-intercept is at 1. That's about all you can really tell on this graph. You'll notice that it kind of runs along like this, and it does go forever, and it just keeps getting closer and closer to the x-axis. It'll never touch the x-axis. So that's something important to note. That's called an asymptote. So an asymptote is something that a graph will get really close to but never touch it. This one would be a horizontal asymptote, because it'll never touch the horizontal line. If you were to spell that, it would be asymptote. So it's a line that you could get close to but never touch. Ours will be on the x-axis. Yeah.
For some reason, there's game graphs on this.
Yeah, they can be confusing. They can be hard to read too.
No, it's not even that they're hard.
That's reasonable. Okay. Now that we know what they look like, we're going to graph a bunch of them and see if we can't figure what the b value is doing as we change the graph. So you'll notice you've got 1, 2, 3, 4 graphs here. I want you to graph all 4 of them. I'm going to do it in 4 different colors, and I'm just going to go in order. So I'll go black, red, green, and blue. So black, red, green, blue. Just so you can easily see which one's which on my graph. I want you to try to write out which one's which, so if you can point to it and say this one's this one, this one's this one, and see if you can't tell what's happening as the b value changes. So go ahead, graph all those things, see if you can't figure it out on your own. If we graph those things, so I have my graphs drawn up there. Let's look at the first two. So we're going to look at y equals 3x and y equals 10 to the power of x. That's my black and my red line. You'll notice that they kind of look like they start off the same, because once you get to the asymptote, the values are so small, they look like they're right on top of each other. You really can't even tell the difference. They actually aren't the same. So they actually are slightly different down here, but you can't even tell that they're different because they're so close together. What you do notice is that they both cross at the exact same point. So they both have a y-intercept at 1. So that doesn't change. What changes is after that y-intercept. So as they come from left to right, you'll notice that they both increase sharply, but one of them is much sharper than the other. The bigger the number, the sharper it's going to be. So you notice that the red one increases more sharply. This one, faster increasing than this one. So the bigger the number, the faster the increase, the faster it turns straight up. If you look at the next two, you'll notice that first off, they go the other way. They're getting much smaller as I go left to right. They also still have a y-intercept at 1. We're going to talk more about that in a minute, but notice that they all do cross the same point. All right, these guys are decaying. The other ones you had exponential growth. These ones are exponential decay or some sort of decrease, whatever word you want to use. I like to use the word decay. They're getting smaller and smaller and smaller as I get further along in the index. Okay? The reason they're doing that is because b is less than 1. So when you have b is less than 1, you have decay. So it gets smaller. When b is greater than 1, you have growth. We're going to talk more and more about growth and decay as well, especially once we get into word problems, because they're going to make sense. You're going to be like, I get it. We want that to increase, so we need a value bigger than 1. We want that to decrease, we want it less than 1. Yeah, Jay.
So, why does, I don't know if you already said this, but why does, like, it comes down to
Why does it come down?
Yeah.
Like this. So if you think about it, let's look at just this one. Y equals 1 over 10 with our x. So if I made x equal to 1, it would equal 1 over 10, correct? If x is to 1. Now if I made x equal to 2, that would equal y equals 1 over 10 times 1 over 10, which equals 1 over 100, which is now a smaller number than 1 over 10. So as the exponent's increasing, I'm multiplying it by another fraction, which makes it a smaller and smaller and smaller number for y. That's why it's decaying instead of increasing. Where the other ones before, because they were bigger than 1, if I went 3 times 3, that's now 9. If I went times another 3, now all of a sudden I'm 27. And if I went times another 3, now I'm a number that's too big for my brain. And it just, I think it's 81. It just keeps going, right? It'll get faster and faster increasing. These will get faster and faster decreasing because the denominator is going to get way bigger than the numerator. Kind of a strange thing to think about, but I mean, it makes sense when you consider fractions times fractions makes smaller numbers. All right, the other thing you're going to notice, which one of these had a more sharp decrease? The green one went a little wider, right? The blue one was much sharper. So that means the closer to 0 you are, the sharper it is. So this one was sharper. Oh, that's the eraser. That one was more sharp. It decreased faster because it was closer to 0. Once your b value is less than 1, the closer to 0 you get, the sharper it's going to be. If you're greater than 1, then the further away from 0 you are, the sharper it's going to be. At the end of the day, what does our b value do? Our b value decides if it increases or decreases. Our b value also dictates how sharp it is. I use the word sharply, but just how quickly you see it decrease or increase. I use the word sharp because people understand that for some reason. It's sharp, that it just like comes straight down. Sharply. I don't know if sharply is a word for it. It sounds cool. So yeah. How sharp. Alright. We can draw some general conclusions about the graph b to the power of x. Where is the x-intercept on all those graphs we just did? There is no x-intercept. There never will be. So there's, sorry, yeah, y-intercept. You knew that. There's no x-intercepts. They'll never cross the x-axis. Well, where's the y-intercept, Jade? For y equals b to the power x graphs, it will always be 1. That will change depending on some graphs, but we'll talk more about y-intercepts. What's the domain for all of these exponential graphs? Yeah, Brian. X is an element of the reals. X is allowed to be any number you want. I mean, you would have to make your graph really big to see what's happening once you got up beyond x equals like 10, but it is possible that x could equal any number. What's the range for these graphs? So if you look back at these graphs, what's the lowest it's ever going to get? 1 would be right there. Does it get lower than there? It goes lower. It gets as close as possible to the x-intercept, but it never touches it. So we would say that y is greater than 0. Not greater than or equal to, because it never actually hits that line, but it gets ridiculously close. So y is greater than 0. Where is the horizontal asymptote? That means a line that goes side to side that you can never touch. It's the x-axis. The equation is y equals 0. So if you drew a line at y equals 0, that would be your horizontal asymptote. It's always there. Yeah.
I think we talked about this like last year, but do asymptotes ever stop?
They would go forever. Yeah.
Okay, but that doesn't make any sense to me because if it goes forever, how does it never touch the x-axis?
The reason why is because of the idea that like we don't know what the biggest number in the world is, and we don't know what infinity is. Right? Like you could always count up one more. Because if you pick any number in the world, like 999 trillion, 999 billion, 999 million, 999,999, you can always add 1 to it. Right? There is no world's biggest number. That's why infinity exists. So this number could extend out forever all the way out into infinity. And it would get so close to 0, but it would never get there. It would just be going down. So it would be 0.00000000001. And then if you wanted to go a little bit further, you could do it again. Just add another 0. And it would go forever, like microscopic. Like you would never be able to measure something that small. Just like infinity, you could never measure something that large. You could always just add one more thing to it. Yeah, it's kind of tricky. Actually, that was when I was in university. Like, you learn a lot of useless crap in math degree. But one of the cooler conversations was the idea of like infinity and what it means and stuff like that, and why it exists and what do you do about it? Because there is no biggest number. But you can always go one more. And when does that become useful, and what do you do with that kind of stuff? Again, useless information, but kind of cool conversations. Kind of blows your mind a little bit. Yeah, it's weird.
Like that, there's more decimal numbers than there are real numbers.
Yeah, good. Okay. Now we're going to figure out what the AB value is. So remember that it's y equals ABX. All those other questions, the A value equaled 1, so it looked like it didn't exist. Now we're going to graph the same graph 4 times, but we're going to change the A value each time. In this first graph, A equals 1. This one, A equals 2. This one, A equals 5. This one, A equals 0.5. And I want you to graph all 4, sketch them. I'm going to sketch them with the 4 different colors again, and we're going to see if we can't figure out what A's do. When you're putting these in your calculator, I like to put them in as like y equals 2 in bracket 3 to the power of x bracket. So that I know my calculator is putting the x on the 3 and not the 2. If you ever have a negative number, then you would go bracket, bracket, -3, bracket, power max, close it off. Your graph should look somewhat like mine. It's hard to graph these things accurately, like really hard to graph these things accurately. Some things that you definitely want to notice when you graph them is the y-intercepts that we used to say were always at 1 are no longer at 1. So in this first graph, where's the y-intercept? If you were to calculate it, it's at 1. In the second graph, if you were to calculate your y-intercept, it's at 2. On the third graph, if you were to graph your y-intercept, it's at 5. And on your last one, if you were to graph it, it's at 0. Why that's true? It's true. The A value is going to give you your y-intercept. Here's my reasoning why it's going to give you your y-intercept. So I'm going to write that down first. The reason why. Let's hypothetically just create an equation that says y equals a, b, r. The y-intercept is when your x value equals, what's the x value for all y-intercepts? It's 0. So if we want to calculate this thing right here, let's change x to be 0. What's anything to the power of 0 going to equal? It'll equal 1. So that means the y-intercept would be at a times 1, which is just at a. So your y-intercept will always be your a value, because anything to the power of 0 is 1, and 1 times anything is itself. So whatever a value you have automatically will be your y-intercept. It also looks like it's making your graph more increase sharply or not sharply. It's really not having much effect on that. It does stretch it a little bit, is what we would call it. It wouldn't make it more sharp all the way through. It's just really hard on an exponential graph to notice that. All it's doing is stretching it. But what I really want you to know, your a value is the y-intercept. What if you have a negative a value? So we're going to take all those graphs we just did on the other page, and we're going to graph them all again, but we're going to change the a value to be a negative a value. So I want you to go ahead and try to graph those. If you graphed all those things, you should have noticed it was the same graphs as the slide before, except they were all flipped upside down. Now, we've talked about this before. We've talked about in other units how the a value flips your graph. The same thing's happening here. So the a value dictates whether you're opening upwards or opening downwards. We had another term for it. So we didn't call it opening up or opening down. We didn't really call it increasing or decreasing. What we did was we called it end behavior. So if a was greater than 0, we went from quadrant 2 to quadrant 1. We call that end behavior. If a was less than 0, we now had quadrant 3, quadrant 4. So A dictates where my y-intercept is also tells me which way I'm opening. Am I going up or am I going down? We almost exclusively have A values that are greater than 0 once it comes down to word problems. Because usually, in word problems, we're talking about things in real number terms, like positive numbers. We talk about the natural numbers a lot. We don't do a lot in the negatives in word problems. It's possible, we just don't do it. So these are the things that A value tells me. It tells me my y-intercept, tells me which way I'm opening up, or it tells me my end behavior. So to summarize everything we know about exponential graphs, we know, and this is kind of a page that's going to be like your little go-to. So the y-intercept is your A value. It was 1 on all those first graphs because A was equal to 1. Now we know that it's actually just equal to whatever your A value is. There's no x-intercepts. You'll never have an x-intercept. The x-axis is a horizontal asymptote. The domain for every graph is x is an element of the reals. The range depends on the A value, which makes sense because the A value told us if we were opening up or opening down, right? So if A was greater than 0, the range was y is greater than 0. If A was less than 0, the range was y is less than 0. Positive A means positive y's. Negative A means negative y's. The value of A and B determine whether you're increasing or decreasing. So we used to say B was depending on if it's increasing or decreasing, but it's not quite true. B tells you how sharply things will increase or decrease. A and B, both in context, are telling you whether it's increasing or decreasing. Yep.
The asymptote is the thing it breaks off of.
Yeah, it's like it like comes up off of it. Yeah.
And it breaks off of the y.
No, not in this case. In future cases, we will. Exponential always have it coming off the x. If A is greater than 0 and B is greater than 1, we had graphs that look like that. So that means the graph increases from 2 to 1. If you look at, I'm going to draw 3. The second situation, A is greater than 0, but B was a decimal. It was opening like that, which means it was decreasing. It was still opening upwards, but now it was decreasing as we went. Remember, that's as we got closer to 0, but it was less than 1. When A was negative, but B was greater than 1. So you're trying to picture what that looks like? A is negative, but B is greater than 1. You should have had a graph that looks like this. So that means that it is decreasing. Notice that the y values are getting lower and lower and lower as I increase. Freaks you out a little bit when you're like, we definitely didn't do the right thing last night. We did do the right thing, we just haven't done it yet. If A is less than 1, but B is a decimal, your graph looks like this. So it's technically increasing as you go from 3 to 4. It's getting really, really close to 0. It'll increase until infinite, all the way up to 0. So the graph increases. We haven't done a graph with one of those, but that's what it looks like. So I've drawn it down here for you. to just kind of picture what it looks like. It's going up as you get further along x, and again, it runs right along that asymptote. The value of b also affects the steepness of the graph. So as b gets bigger and bigger and bigger than 1, we say that it gets steeper as b increases. So the bigger the b value is, the more it increases. That's assuming it's bigger than 1. So the further away from 1 it gets, the more it increases. Now when you're the other way, and you're less than 1, then it's getting steeper the closer it gets to 0. So when b is in between 0 and 1, the curve gets steeper as b decreases. Because it's getting closer and closer to 0, which makes it sharper and sharper and sharper. This page basically tells you everything you need to know about exponential graphs. Like, all your info is there. Logarithmic graphs. Logarithmic graphs are very similar to exponential graphs, which makes sense because logs and exponents are linked, right? Remember that you're really just changing form in between logs and exponential. So the graphs should probably also be linked. And what we're going to do is we're going to try to graph one just to see what it looks like. So if you graph y equals log 2 of x and see what it looks like, in your calculator that means y1 equals bracket log x divide by log 2. Remember, you have to put things in your calculator as 2 separate logs where the base goes on the bottom. So if I was to graph this thing, I would go log x divide by log 2. If I graph it, it looks like this. And it actually would go on forever. This is a little bit different than our other graphs. Our other graphs would start off by running along the x-axis and then go up. This graph starts by running along the y-axis and then it goes off to the other direction. These things are called inverses of each other. You need to know nothing about inverses in this class. But what an inverse means is that it's reflected. And this is reflected on an axis. That's a perfect diagonal. So these graphs are literally just flipped mirror images of each other. You need to know nothing about them. It's just kind of cool image for you to be able to see that they're actually opposites of each other. If they're opposites of each other, that means instead of having an x-axis as an asymptote, where's my new asymptote going to be? It's going to be my y-axis. So now I have a vertical asymptote when I do log graphs. Okay, so log graphs have vertical asymptotes. You'll also notice that this thing increases not nearly as sharp as the other graphs. The other ones kind of went way up into infinity. These ones kind of taper off and go really far out to the x's without increasing much of the y's. To figure what the b value does in a log graph, we're going to graph a whole bunch of those things. So you're going to graph them, see what the b value does. All you're doing is you're changing the base. See if you can't see how these graphs change. So looking at these log graphs, as you change your b value, what you should have noticed is that they were either getting steeper or not quite as steep, like they were turning sharp, right? So if you look at the first two, you notice that they go from 4 to 1. Right? That's how the graphs go. And you'll notice that as b got smaller, 3 was the smaller one, that it didn't go as sharp along the x-axis this time. So before we were talking about how it would turn up really fast. Now, as b gets bigger, it turns to the right really fast. So b gives you your curve to the right on how sharp you're turning to the right. When you rotate into these numbers, which are less than 0, you notice that the direction of the graph changes. So now it's going from 1 to 4, so it's affecting your end behavior. And you're also going to notice that it turns sharply as you get closer to 0. So just like b value on exponential graphs determined how sharp things were happening, same thing's happening here. It's determining how sharp things change. So if you're greater than 1, the further away from 1 you get, the sharper it is. The closer you get to 0, if you're less than 1, the sharper it is. So the b value is affecting the rate of change or how sharp it is. But it's the exact same concept. So there's probably not a coincidence that the b value does the same thing in both graphs. Because remember, the b value is the base for exponential and for logs. It's the same number. For all graphs like this, if you looked at those other graphs, would you notice with the x-intercept? They should have all been, they existed when it first up. No, they do exist. The x-intercepts all existed at 1. And now it's the y-intercepts that don't exist. Remember, these graphs are like opposites of each other, inverses. They're completely different. So we used to have y-intercepts, now we have x-intercepts. We used to have x-intercepts, now we have y-intercepts, right? That don't exist. The domain of these things is now x is greater than 0, because it'll never touch the y-axis, which is where x equals 0. The range is now y is an element of the real, the complete opposite of where our exponential once was. Notice how the x's and the y's have all just flipped. That's called an inverse. The vertical asymptote is now at x equals 0. We used to have a horizontal asymptote at y equals 0. So literally, it's like y and x have just swapped places with each other, and that's what inverse graphs do. They just rotate where your x and y values are. All right, to figure out what the a value does. So if you're looking at graphs that are like this, we have 4 graphs here. Some of them are positive, some of them are negative, some of them are decimals, some of them are not. I want you to graph all 4 and see what you observe. Okay, so if I graph all those things, you're going to notice a little something about our a value. Our a value on our last question told us what our y-intercepts were. Our a value in these questions, did it change our x-intercepts? No, it didn't change our x-intercepts. Okay, so that's a little bit different for us. So that's something that's not opposite of each other. But what it did change was our end behavior again, right? So it changed whether I was going to open upwards or open downwards. You'll notice that these two both went from quadrant 4 to quadrant 4. It also did make it a little bit steeper, a little bit less steep, so it stretched it again. Okay? These two open upwards, or what we would say is went from quadrant 1 to quadrant 2. Now, if you had a negative a value and a b value that was less than 0, it would flip itself like twice, right? Just kind of like it did in the last one. But what our a value is doing is it's flipping our graph, it's affecting which way it's opening upwards. To draw some conclusions about our little log graphs, we can't draw nearly as many. Okay? The first thing we can say is that our x-intercept is at 1. and that there is no y-intercept. So that's opposite of each other. The domain now is x greater than 0. And if you look, it was true for all of our graphs. We never were facing the other way. The range is now y is an element of the range. The y-axis is a vertical asymptote. The equation is x equals 0. So that's a little bit different than before, right? That's x equals 0. We have our 4 situations again. If a is greater than 0, if b is greater than 1, what's it look like? We have if a is greater than 0, if b is in between 0 and 1. And then we have the same thing if a is negative. If you're ever not sure, you could always just graph it, right, and see what it looks like. It wouldn't be that hard to do. Right? Just pick some numbers that are greater than 0 and greater than 1 and graph it and look at it. Yeah. Yeah, actually, this stuff that we are doing right now, the word problems we do, are like very, very applicable to the real world, which is kind of cool. Some common things that you'll see is it's very applicable to the growth of like bacteria or something, which is exponential, or even the population of humans is exponential around the world. Something else that's very applicable would be the depreciation of a vehicle or something like that, because it sharply gets worse.
No, but it can go back up. It's like 5 people.
It can sometimes go up. Yeah, depreciation of vehicles is also spot on. Something else it's really good for is interest rates. So if you want to see like what your bank account would look like if you made this much interest, or if your Visa bill, which is what you guys are going to have one day, has an interest rate, what happens when you don't pay it off? And it follows exponential curves like these ones. And then log curves. Log curves are super applicable to comparing things. So you know how you guys talk about pH scales in science? pH scales follow log curves. Earthquakes. So earthquakes follow the Richter scale. The Richter scale, that's yours. Your scale is based off of logs. Yeah, so it's kind of cool. Okay,
We talk about asymptotes in chemistry too.
Yeah.
They did say.
Okay. The way that these things open up depends on your A and your B value. If you're never sure, because to me the log ones are more difficult to remember, the B ones will be more common sense. So the A ones, I wouldn't blame you at all if you just graph them and check. If you want to memorize this, sure, that's fine. But I'm A-okay with graphing and checking. So if you wanted A is greater than B, 0, and B is greater than 0, then you're looking at a graph like this. A is greater than 0, B is greater than 0. Right? If you wanted to see A is greater than 0, B is less than 1, you're looking at something like that, which now switches and goes the other way. Okay, so if you were doing the first ones, you would say it's increasing. So as I go from 4 to 1, I'm getting bigger. If I was going the other way, as I go from 1 to 4, I'm decreasing. The next two, if A is less than 0 and B is greater than, then you're looking at the green and the blue line. Right? That's an A value that's less than 0 and B value greater than. So that means you would have a graph that is decreasing. Now we didn't do the other one, just like we didn't do the fourth one before, but all it is it's flipped one more time. So you flipped it and then you flipped it back, so it would be increasing. And you could draw little sketches on the side if you want to match each one up. Right, that's like an intro into what these graphs are going to look like. We're going to spend 2 days figuring out how to use these graphs and why they're useful to us. Okay? Awesome.